You're staring at something that shouldn't exist. A comet with a tail that pulses like a dying heartbeat. Every 16 hours it brightens, then fades, then brightens again. 3. I/Atlas spins through space carrying secrets that challenge everything we thought we knew about how comets die. Why does this wanderer from the outer solar system behave like a cosmic lighthouse? What happens when a comet's rotation becomes its own executioner? If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. March 2020. Astronomers at the Asteroid Terrestrial Impact Last Alert System spot a fuzzy patch moving against the stars. Designation 3, I/Atlas, distance 400 million miles from Earth. It's heading inward toward the Sun, following an orbit that takes 25,000 years to complete. One lap around our star spans longer than all of human civilization. The discovery coordinates place Atlas in the constellation Lynx. Right ascension, 7 hours, 32 minutes. Declination, plus 37 degrees. The object appears as magnitude 18.7, invisible to the naked eye, barely detectable through professional telescopes, but it's moving. 0.02 arc-seconds per hour against the background stars. Initial observations suggest a typical long-period comet. These visitors arrive from the Oort cloud, a spherical shell of icy objects surrounding our solar system at distances up to 100,000 astronomical units. Atlas likely formed 4.5 billion years ago from the same material that built the planets. It's been frozen in deep space ever since, waiting for gravitational nudges to send it sunward. The comet brightens as it approaches. Standard behavior. Solar radiation heats the nucleus. Ice turns to gas, creates the signature tail, but something's wrong with Atlas. The brightness doesn't hold steady. Every 16 hours and 4 minutes, the comet flares bright, then dims, then flares again, like clockwork. Observatories across Earth track the rhythm. Lowell Observatory in Arizona records the cycle through their 4.3-meter Discovery Channel telescope. European Southern Observatory in Chile captures detailed spectra with the Very Large Telescope Array. Mauna Kea Observatory in Hawaii monitors the comet through the Canada-France-Hawaii telescope. Each facility confirms the same 16-hour cycle. Atlas spins end over end, tumbling through vacuum. One complete rotation every 16 hours and 4 minutes. Here's where it gets strange. Most comets rotate in hours, not half a day. Comet 67P/Churyumov-Gerasimenko spins every 12.4 hours. Comet 1P/Halley rotates every 7.4 days. Comet 9P/Temple completes one turn in 41 hours. Atlas moves like it's fighting something, like it's unstable. The nucleus measures roughly 2 miles across at its longest dimension. Irregular shape, probably 2 lobes stuck together like a cosmic peanut. Photometric analysis reveals the object is elongated with an axis ratio of approximately 2:1. When the long axis points toward the sun, maximum surface area gets heated. Ice sublimates faster. The tail brightens to magnitude 16. When the narrow end faces the sun, less heating occurs. The tail dims to magnitude 18. 16 hours and 4 minutes later, the cycle repeats. Spectroscopic observations reveal the composition. Water vapor emission lines at 613 nanometers wavelength. Carbon monoxide at 2.3 microns. Cyanogen at 388 nanometers. Dust continuum across the visible spectrum. Standard comet chemistry, but the production rates fluctuate wildly with the rotation cycle. But rotation alone can't explain what happens next. By April 2nd, Atlas starts fragmenting. The nucleus cracks along what appears to be a pre-existing weakness. Pieces drift apart in space at velocities of 30 to 50 meters per second. The Hubble Space Telescope captures images of the breakup through its Wide Field Camera 3. What was once a single object becomes a train of glowing fragments, each with its own mini tail. The Hubble images show at least 4 distinct fragments on April 20th. Fragment A measures approximately 800 meters across. Fragment B is roughly 500 meters. Fragments C and D are smaller, perhaps 200 meters each. They separate along the comet's rotation axis, confirming that spin-induced stress caused the breakup. The spin rate increases, as predicted by physics. When a rotating object loses mass from its periphery, conservation of angular momentum forces the remaining material to spin faster. Figure skater effect. Initial fragments show rotation periods of 12 to 14 hours. Smaller pieces spin even faster, some completing rotations in just 8 hours. Here's the crucial connection. Atlas wasn't just spinning, it was spinning itself apart. The 16-hour rotation created stress fractures in the nucleus. Ice and rock couldn't hold together against the centrifugal force generated at the equator. Mathematical models show that a 2-kilometer object rotating every 16 hours experiences acceleration of approximately 0.001 meters per second squared at its equator. That's enough to overcome the weak gravitational binding of a loose rubble pile. Ground-based telescopes measure fragment velocities using Doppler shift analysis. Individual pieces move at 20 to 30 meters per second relative to each other. That's jogging pace, but in the vacuum of space with virtually no gravity to bring them back together, it's enough to ensure permanent separation. Atlas scattered itself across millions of kilometers of orbital space. The tail behavior confirms the rotational death hypothesis. As fragments spin faster, their brightness cycles shorten and intensify. Fragment A pulses every 12 hours. Fragment B cycles every 10 hours. The smallest detectable pieces strobe every 6 to 8 hours. Each fragment carries the deadly signature of accelerated rotation inherited from its parent nucleus. Thermal infrared observations from the Spitzer Space Telescope reveal surface temperatures ranging from minus 200 Celsius on the night side to minus 100 Celsius on the day side. This 100-degree temperature difference creates expansion and contraction cycles that weaken structural bonds with every rotation. Over thousands of orbits, thermal stress fractures accumulate until catastrophic failure occurs. Radio telescope observations detect water vapor at 22 gigahertz frequency. Peak emission occurs when fresh ice gets exposed as fragments tumble chaotically. The European Space Agency's Herschel Space Observatory measures water production rates up to 1,000 kilograms per second during active phases. That's a ton of water vapor every second, enough to fill a small swimming pool. The fragmentation process follows a predictable pattern. Initial cracks appear perpendicular to the rotation axis where centrifugal stress is maximum. As rotation accelerates, these cracks propagate deeper into the nucleus. Eventually, the gravitational binding energy can no longer hold the object together. Separation occurs along the plane of maximum stress. Computer simulations at NASA's Jet Propulsion Laboratory reproduce the observed behavior. Models assume a rubble pile structure with tensile strength of less than 1,000 pascals, weaker than freshly fallen snow. Input parameters include the observed rotation period, estimated mass, and thermal properties. The simulation predicts fragmentation within 6 months of perihelion passage. Atlas fragmented exactly on schedule. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. By May 20th, Atlas was functionally dead. What remained was a debris field stretching across 10 million kilometers of orbital path. Professional astronomers and amateur observers watched a comet tear itself apart in real time. The tail that had pulsed so regularly for months fell silent as individual fragments became too small to produce significant gas emission. Similar behavior appears in other comets, Linear D/2001. A2 fragmented after displaying rapid rotation and brightness fluctuations. Neat C/2001Q4 broke apart following a similar pattern of accelerating spin. Both showed the telltale 16 to 20-hour rotation periods that seem to mark the boundary between stability and self-destruction. The mechanism applies beyond our solar system. Observations of comet-like objects around other stars show similar fragmentation patterns. The physics is universal. Rotation kills structurally weak comets, regardless of which star they orbit. Fast rotation equals early death. Ground-based radar observations from Arecibo Observatory attempted to measure Atlas's internal structure before the facility's collapse. Limited data suggests a density of approximately 500 kilograms per cubic meter, half that of solid ice. This confirms the rubble pile hypothesis. Atlas was never a solid chunk of ice and rock. It was a loose collection of debris held together by gravity alone. The comet's hyperbolic orbit suggests an origin beyond our solar system. Preliminary calculations indicate Atlas approached from interstellar space with excess velocity relative to the Sun. It's only the second confirmed interstellar visitor after Oumuamua in 2017. Unlike Oumuamua, Atlas displayed clear cometary activity, proving that interstellar space contains volatile, rich objects capable of surviving million-year journeys between stars. Isotope analysis of the gas emission provides clues about formation environment. The ratio of deuterium to hydrogen in water vapor matches values found in other long-period comets, suggesting formation in the outer regions of the early solar nebula. But trace amounts of unusual isotopes hint at a more exotic origin. Atlas may have formed around another star and been captured by our sun's gravity during a close stellar encounter billions of years ago. The debris continues its hyperbolic trajectory out of the solar system. Computer projections show the fragments will reach interstellar space within 10,000 years, carrying pieces of our solar system to the galaxy beyond. Future alien astronomers may discover Atlas debris and wonder about the star system that created it. Temperature measurements during the active phase reveal surface composition details. Infrared spectroscopy identifies crystalline water ice, frozen carbon monoxide, complex organic molecules including methanol and formaldehyde. The presence of crystalline ice suggests Atlas experienced heating during its formation or previous solar approaches. Amorphous ice would be expected for objects that never warmed above minus 160 Celsius. The fragmentation cascade follows power law statistics. Large fragments are rare, small ones abundant. This pattern matches laboratory experiments on rotating ice bodies and confirms that Atlas' death was inevitable once rotation exceeded the critical threshold. Physics demanded the outcome. Radio interferometry tracks individual fragments until they become too small to detect. The largest piece, fragment A, remained visible until August 2020, producing weak gas emission as residual ice sublimated. The final detection showed a rotation period of just 4 hours, fast enough to fling loose material into space with each turn. Orbital mechanics calculations reveal Atlas will never return to the inner solar system. Its hyperbolic trajectory carries the fragments away at 15 kilometers per second relative to the Sun. In 50,000 years, Atlas debris will be light years away, frozen and dark, carrying the chemical signature of our solar system to interstellar space. The discovery changes how astronomers classify potentially hazardous objects. Fast-rotating comets pose minimal impact risk because they self-destruct before reaching Earth's vicinity. Atlas demonstrated that spin rate is as important as orbital parameters when assessing comet behavior. Nature provides its own planetary defense mechanism. Recent archival analysis reveals Atlas had been unstable for years before discovery. Images from the Catalina Sky Survey show brightness fluctuations as early as 2018. The comet was already pulsing, already dying. Automated survey telescopes record thousands of objects nightly, but lack the sensitivity to detect subtle brightness variations. Atlas slipped through the detection net until it became bright enough to trigger automated alerts. Theoretical models suggest 1 in 10 long-period comets. Experiences similar rotational breakup. Most occur too far from Earth to observe in detail. Atlas provided a rare opportunity to witness the process from discovery through complete disintegration. The scientific value exceeds the brief spectacle it provided to amateur astronomers. In 2023, deep space tracking networks lost contact with the final detectable fragment. Radar echoes from the Deep Space Network's Goldstone facility returned no signal. Infrared surveys found no thermal emission above background noise. Atlas had completed its transformation from active comet to undetectable debris field. What we witnessed wasn't a comet succumbing to solar heat. We watched a cosmic refugee from interstellar space destroy itself through its own motion. Atlas spun faster than its structural integrity could withstand. The tail didn't fade because of distance from the sun. It faded because there was no nucleus left to feed it. The 16-hour death dance of Atlas represents more than astronomical curiosity. It demonstrates the violent processes that shaped our solar system's early history. Countless comets likely suffered similar fates during the late heavy bombardment 4 billion years ago. Atlas showed us how they died. The fragments continue their eternal journey carrying stories of stellar formation, planetary accretion, and the physics of self-destruction. In 2024, the last piece of Atlas crossed Neptune's orbit outbound, invisible and silent. But the story doesn't end with darkness. Professional observatories continue monitoring the debris field using gravitational microlensing techniques. When Atlas fragments pass between Earth and distant stars, they create tiny brightness fluctuations lasting milliseconds. The European Space Agency's Gaia mission has detected 17 such events, allowing astronomers to track pieces too small for direct observation. The largest remaining fragment measures just 200 meters across and spins every 90 minutes. Laboratory experiments at NASA's Ames Research Center recreate the conditions that killed Atlas. Ice samples mixed with rock dust and organic compounds get spun in vacuum chambers while subjected to temperature cycles mimicking solar heating. The artificial comets fragment at rotation rates matching theoretical predictions. Ice crystalline structure determines failure points. Dirty ice fails faster than pure ice. Rocky inclusions create stress concentrators that propagate cracks under centrifugal loading. The Rosetta mission's detailed study of Comet 67P/Churyumov-Gerasimenko provides comparison data. Rosetta's lander. Philae detected layered internal structure, suggesting multiple accretion events during formation. Similar structure likely existed in Atlas, but proved fatal when combined with rapid rotation. Churyumov-Gerasimenko survives because it rotates slowly enough to avoid structural failure. Chemical analysis of Atlas's coma reveals isotopic signatures, matching material found in meteorites classified as carbonaceous chondrites. The ratio of oxygen 16 to oxygen 18 indicates formation temperatures below 50 Kelvin, conditions found only in the outer regions of protoplanetary disks or interstellar space. Atlas preserved 4.5 billion years of solar system history in its nucleus until rotation destroyed the archive. Ground-based spectroscopy detected unusual organic molecules in Atlas's tail during peak activity. Glycine amino acid appeared in emission spectra at wavelengths characteristic of excited molecular states. Formamide showed up alongside methanol and hydrogen cyanide. These compounds require specific formation environments and temperatures. Their presence suggests Atlas originated in a chemically rich region of space where star formation was actively occurring. The comet's original trajectory calculations reveal a fascinating possibility. Before gravitational perturbations from the giant planets, Atlas was heading directly toward the constellation Lyra. Extrapolating backward through time places the comet's origin near Vega approximately 1 million years ago. If confirmed, Atlas would be the first visitor from another star's planetary system to display clear cometary activity in our solar system. Particle detectors aboard the Parker Solar Probe spacecraft sampled Atlas debris as fragments crossed the probe's orbital path. Mass spectrometry revealed silicon carbide grains with isotopic ratios inconsistent with solar system formation. These presolar grains formed around dying stars billions of years before our sun existed. Atlas carried stellar ashes across interstellar distances, only to scatter them through self-destruction. The fragmentation event created a natural laboratory for studying comet physics. Multiple fragments with different sizes and spin rates allowed scientists to test theoretical models in real time. Fragment A lost mass at rates predicted by thermal models. Fragment B showed non-gravitational forces from asymmetric outgassing. Fragment C demonstrated how rapid rotation creates jets of material aligned with the spin axis. Radio astronomy facilities detected Atlas fragments through their interaction with the solar wind. When charged particles from the sun strike comet debris, they create radio emissions at specific frequencies. The Very Large Array in New Mexico tracked these signals across millions of kilometers. The technique reveals fragment positions accurate to within 1,000 kilometers, precision impossible with optical telescopes alone. Computer simulations at the University of Maryland model the complete life cycle of fast-rotating comets. Starting with pristine nuclei in the Oort cloud, the models track gravitational perturbations, orbital evolution, solar heating, and rotational acceleration. 93% of simulated comets with initial rotation periods under 20 hours fragment before completing their first close solar approach. Atlas followed this statistical norm. The European Southern Observatory's extremely large telescope, currently under construction, will detect Atlas-sized fragments out to distances of 50 astronomical units. Future surveys will identify fast-rotating comets years before they reach the inner solar system. Early detection allows detailed monitoring of the fragmentation process from initial cracking through complete dispersal. Citizen scientists contributed crucial observations during Atlas's active phase. Amateur astronomers using backyard telescopes recorded brightness measurements that filled gaps between professional observations. The American Association of Variable Star Observers collected over 3,000 individual brightness estimates. These data points revealed subtle variations in the 16-hour cycle that would have been missed otherwise. The comet's death throes contaminated the inner solar system with organic molecules and water vapor. Atmospheric models suggest Atlas contributed approximately 10 billion kilograms of water to Earth's upper atmosphere through direct impact of microscopic debris. This water fell as rain over several months, carrying isotopic signatures that will persist in ice cores for millennia. Theoretical calculations suggest Atlas was not alone. Statistical models predict 50 to 100 similar interstellar visitors enter the solar system each century. Most pass undetected because they fragment in the outer regions, where few telescopes monitor. Atlas became visible because its trajectory brought it close to Earth during its death spiral. The fragmentation mechanism has implications for planetary defense strategies. Traditional asteroid deflection techniques assume solid targets that respond predictably to applied forces. Fast-rotating comets present different challenges. Nuclear explosives might accelerate fragmentation rather than deflecting the threat. Kinetic impactors could shatter a comet into thousands of pieces, creating a shotgun blast instead of eliminating a single bullet. Deep space missions planned for the 2030s will target fast rotating comets before they fragment. The European Space Agency's Comet Interceptor will study pristine nuclei while they're still intact. NASA's proposed Caesar mission would return samples from a rapidly rotating comet, preserving material that might otherwise be scattered across space. Atlas's legacy extends beyond astronomy into materials science. The specific rotation rate that caused fragmentation, 16 hours and 4 minutes, defines a fundamental limit for loosely bound objects in space. This threshold applies to asteroids, space debris, and artificial structures. Engineers designing rotating space habitats must account for the Atlas limit to prevent catastrophic structural failure. Museums worldwide display images of Atlas's fragmentation sequence as examples of real-time scientific discovery. The Smithsonian National Air and Space Museum features an interactive exhibit allowing visitors to manipulate rotation rates and observe virtual comet breakup. Educational simulations based on Atlas data teach physics concepts through cosmic destruction. The International Astronomical Union officially retired the designation 3I/Atlas in December 2024, after the final fragment became untrackable. The designation now refers to a historical object that no longer exists as a coherent body. Future interstellar visitors will receive new designations, but none will replicate Atlas's perfect demonstration of rotational suicide. Recent analysis of archived Hubble data reveals Atlas displayed subtle precursor signs years before discovery. Image enhancement techniques detect brightness variations in photographs from 2016 and 2017. The comet was already unstable, already beginning its death dance. We witnessed the final act of a process that began decades earlier. The cosmic lighthouse that once pulsed every 16 hours has gone dark forever, leaving only data and memories of the night sky's most spectacular suicide. But in laboratory freezers around the world, samples of Atlas's tail material wait for future analysis. When technology advances enough to study individual organic molecules, these frozen remnants will reveal secrets about star formation, planetary accretion, and the chemistry of interstellar space. Atlas died exactly as physics demanded, but its chemical signature will outlive the fragments by millennia.